Okay, so this is our sixth, I think last chapter on this particular theme of, some problems are easier, some problems are harder, what's going on there. Although we'll carry it with us, for the rest of class. The start of this story was these kind of Boolean algebra problems. I give you some formula in a Boolean logic, ands, ors, nots, and you just want to find inputs that make it output true. Okay? In that full generality, that seems hard because that's like saying basically any logical puzzle, can you solve? But also, yeah, it's a big question. Is there an algorithm for this? We don't know. But maybe what's more surprising is that when you even look at special cases like things in CNF form or 3-sat, where you only have 3 variables in each clause, even that remains pretty difficult. We push it even further to 2-sat versus max 2-sat. 2-sat you can do really fast. Max 2-sat, somewhere in that max was like half a degree of freedom. That seemed to make it hard again. It's Thursday? Yeah, okay. So last Tuesday, we did subset sum, which is a simple looking problem involving numbers. And the surprising thing is that that can be used to solve SAT. And then we did the longest path problem, like Hamiltonian path. We also showed this can be used to solve 3-sat. And that was some very clever, graph that looked like a ladder. Okay, and these are all kind of surprising because longest path doesn't look that different from shortest path on the surface, right? But shortest path or shortest walks we can deal with. Longest path, for some reason, we cannot. And the last time we did independent set, we looked at it in general graphs, but we also looked at interval graphs and very briefly trees. And the theme there was in full general graphs, you can use that to solve 3-sat as well. But intervals actually and trees, they both have more structure. And when you have more structure, there's a chance that actually you can solve it. In that case, there was enough structure. Okay, so, right. Okay, so, one thing kind of that all these problems have in common is that they're sort of like search problems in the following sense. Take like Hamiltonian path, right? Okay, I'm not really sure how to find a Hamiltonian path, but when I find it, it's easy for me to recognize it. Right? The hard part was finding a solution, but it's very easy to write an algorithm that says, can you check to see if this really is a Hamiltonian path? You just check to see, you visit all the vertices exactly once, those are really edges, things like this. That would be very easy to do, right? Maybe subset sum is even easier. It's not clear how to actually find a subset that adds up to the numbers. But as far as double checking an answer goes, right, that would be very easy. If someone just gave you a set of numbers and said, I think this is the answer, you could easily write some code to check it, right? So there's search problems, like in the sense that you can recognize the solution when you see it. It's not clear how to find it, but you can recognize a solution if you do stumble upon it. Okay, and that's sort of one thing that they have in common, and actually that alone is going to allow us to make some pretty strong statements. Okay, so right, so yeah, so we have a typical kind of theorem that we've been doing in the past few weeks is something like this, right? If you have a polynomial time algorithm for, say, independent set, then you'll get a polynomial time algorithm for SAT. And the usual kind of construction is, well, okay, so you're claiming, to prove this, we want to show that if you could solve independent set, then you could solve SAT. So you say, okay, give me any SAT formula. I'll find some clever way to turn it into an independent set problem, so that if we use this algorithm we're proposing, the answer to the independent set problem will somehow reflect correctly upon the original SAT problem, right? So, by coming up with a efficient algorithm that converts SAT problems to independent set in a way that sort of is faithful, yes maps to yes and no maps to no, we've demonstrated that independent set could be used to solve SAT, and if you're willing to believe that SAT is really hard to solve, well, then this will suggest that independent set is going to be really hard to solve as well. Okay, but that's sort of the typical kind of setup. But let's like okay, right? Okay, so all right, so yeah, we're gonna end in a pretty dramatic place, but I'm gonna work in 2 parts. Okay, so the first part of this story is I'm going to try to argue that every polynomial time algorithm is really a polynomial size circuit. Okay, and okay, that's a little bit vague, but I'll explain. And we're going to work in some like very simple kind of idealized model of a computer, which just has like a CPU and RAM. I'll explain that in a moment. But first, does anyone know what this is? Come on, you're all CS students. It is a computer. Okay, great. Does anyone recognize what computer it is? It's a very significant computer historically. Does anyone want to guess what roughly time range it comes from? It's actually from the 70s, not the 80s. 80s is like the Macintosh and the Lisa. What are some like famous old computers you've heard of? Huh? An Atari. No, it's not an Atari. It's not an IBM. I think IBM was largely making mainframes. So much bigger than this. This is like really the size of like a desk. Yeah. Ah, okay. So this is the Xerox. Do you know what the name of the lab was? Okay, so the computer's called Xerox Alto. It was made at Xerox PARC. What does PARC stand for? Palo Alto Research Center. Okay, so somewhere like in the 60s or something, Xerox was like, oh, we should get into this computer thing. And they made this research park, actually early 70s in Palo Alto. And they were very innovative there. But they had this dream of trying to make a personal computer, right? Or this thing they sometimes call it Dynabook or something like this. Before really there was personal computers. Yeah, but they had some kind of like idea of a thing. And so they innovated quite a bit, including, this is like the first GUI. Okay. This is like where Smalltalk was made, which is sort of the first object-oriented programming, or sort of message-based. There's a lot of innovations that came. Oh, Ethernet they also made at Xerox PARC. They were trying to like imagine like an office of the future with all these little computers like wired up. So they have some like primitive form of email. They also did like desktop publishing for the first time, something that looked like Microsoft Word. And they were doing this in the 70s, right? So like the Apple II is like what, 77, 78 or something, and Apple II is just a terminal, right? So this is the famous thing that Steve Jobs and Wozniak got to take a tour of the lab in like 81 or something, and they saw this and they came back and they're like, oh, we have to actually build a real computer, not this Apple II thing. In exchange for the tour, Xerox got some stock in Apple or something. It was before the IPO. Okay, anyway, you should all know this. You should all go watch talks by Alan Kay, which is always very inspirational. But of course, that's besides the point of this lecture. Although that alone maybe is good enough. All right, so we're going to talk about an idealized computer with just CPU and RAM. I could potentially make this lecture much more rigorous, where it's like, I'm going to define something called a Turing machine. It's going to be very formal and stuff, but you're going to get so bogged down in details, you'll kind of miss the forest for the trees, and you're not really losing any essential things when I give you this kind of simpler version here. So in our very simple model of a computer, I'm just going to assume I have memory and CPU is just like some kind of big circuit, which it is. It's just a hunk of metal. And we're just going to assume like in every step of a program, that CPU is going to just like read a couple of, a finite number of locations of memory. I just did 2 for simplicity, and it'll write to 1. Right? And if you like think about it, that's enough to like load registers and read instructions and all this stuff, right? So you don't lose much generality. So I guess here, like x410 is equal to x2, 3, x7, whatever. So maybe you'll read in from like here. And I always get this wrong. So the 7th row is like down here. And then I think there's actually 18 columns because I made 20 lines once. And anyway, it's not worth recounting. But you just read 2 locations from memory. And then you write to, 1 location from memory, I guess 4, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like this. Okay, and that's how I'm just going to think of a computer, and I'm going to think of a program for sake of discussion as something doing a bunch of this stuff in a row. Okay. All right, so yeah, I want to argue that somehow every kind of program is sort of like a circuit. All right, and this is sort of a awkward question because it's very abstracted, but still, I would say there's sort of maybe one really key difference between how I define a circuit and how I've sort of defined this idealized computer. Anyone want to take a stab at it? What they have in common is that like they read some finite thing, they write some limited thing. Yeah, again, the model might be too abstract to think, but there's kind of one key conceptual difference, I'd say. Yeah.
Is the circuit right to anywhere at all?
Yeah, I think write to anywhere or where it writes. If I think of like a circuit kind of propagating up and stuff like this, it's always writing to a new location. Like when we think of a circuit, we always think of like creating a new node for every like intermediate output. But a computer can kind of like write over the same spot in memory, right? Otherwise, it's kind of very simple. If I imagine all the steps of the computer, it's reading, it's writing, it's reading, it's writing. I could also imagine something like this. But I think one key difference is that in this model, you can actually rewrite to the same location in memory and override previous things. Whereas somehow circuits, we just disallow that because that would be like not a DAG anymore. And yeah, right? Okay, so at some level, like, yeah, I'd say that the CPU is allowed to write to the same location in memory. And like, if you were trying to think of it as a circuit, I'm trying to argue that effectively every program is a circuit. But you would say, well, if you're writing to the same location in memory, then like if I had imagined kind of creating a circuit where every memory and location is like a node and I can have certain operations, because ultimately this is just some kind of circuit, right? So it's some complicated version of this thing. But if I had tried to make some kind of auxiliary graph, then I can imagine getting lots of cycles from reading and writing to the same location. Right? Again, I'm speaking a little bit abstractly, but so I'd say that's the big conceptual difference. So I guess the question is, how, again, we are proving something a little bit confusing, but I want to try to argue that every polynomial time algorithm can be thought of as a circuit. But really, I want to first say that anything that runs on a computer can be interpreted as a circuit, and then we'll worry about size later. But the kind of blocking thing is that at least the first thing I see is I'm reading and writing to the same location in memory. That seems different than a circuit. Yeah.
What if when you try to override something, you really in the circuit create a new node with like duplicate connections to like output connections, I guess.
Yeah, if I just always wrote to a new location, then that wouldn't be an issue, right? Okay, so if I had some kind of like, if my program was set up to never write to the same location, then it would be okay.
But even if you have a program that overwrites it, you would just translate that as writing to a new node in the circuit.
Okay, can I like somehow compile it or think of it as right? Yeah, so how can I do that?
You would have to somehow know how many. If you had to create this circuit beforehand, then you would have to think of how many times am I going to override this memory position. Assuming that you have a finite number of overwrites, you can create a finite number of nodes and just say the first time I write here, then it's this node. The second time it's this node. Just keep going. And you just kind of connect the outputs of those nodes to whatever they have to be used for.
Okay, so if I had like a very sophisticated compiler or something that can look at my program and said, oh, this variable is going to get overwritten 15 times, then I should make like 15 copies, one for the first time, second time, third time, fourth time, fifth time. But so that would work, but that seems like a high demand on a compiler, right? So I do kind of want to do this, but I want to maybe do it in a little bit more of a, I guess, naive way, clumsy way. That doesn't necessarily require us to like, statically analyze a program. First of all, I think that's incomputable, but like, kind of thing. So if there's like a trick way to do this, okay, so maybe as a hint, there was maybe one time before where it felt like we were trying to do something simple, but there was something related to cycles that was making things very confusing. And I would say that was when we were doing like negative length shortest paths and Bellman-Ford, right? And like Dijkstra doesn't work. You can't just visit things once, things get confusing and things like this. You have negative cycles and stuff, right? So, you could try lots of direct algorithms, you never get anywhere. So how do we circumvent this for that problem? How do we resolve negative length shortest paths when Dijkstra didn't work? Or maybe I should be just more, yeah. We just parameterize by time, right? If you try to do a direct algorithm like Dijkstra, it gets very confusing trying to keep track of negative edges and stuff. But if you just say, what's the best in 2 steps, 3 steps, 4 steps, 5 steps, then the algorithm is very simple, right? There's none of this risk because we just added another dimension. And over time, there's essentially no cycles, so to speak, right? So that is what we're going to do, okay? So I can imagine taking my program, which has some number of steps, and even lazier than trying to analyze and anticipate how many times a variable gets used, I'm just going to copy the whole memory over and over and over with every time step. Right? This is really more of a thought experiment. It's not going to get you like the tightest bounds or anything, and that's not too important for us. So I imagine like if I want to kind of take this computer thing that's reading and writing to the same location, I'm just going to think of like unrolling by time. And now when I go from time 1 to time 2, I'm imagining I copy over everything and I just update in the second one whatever the CPU updated. Okay, so just copy everything over, and then you don't have to do something sophisticated like stare at the code and say, oh, this will get used 15 times or whatever. I'll just keep copying, keep copying, keep copying. Okay, but this is kind of very similar to sort of the Bellman-Ford trick. Okay, we're just going to parameterize over time, and now there's no confusion about reading and writing to the same location in memory. Okay, so yeah, so kind of implicitly, there's like a bunch of hidden arrows in parallel where all the other locations just get copied over. Okay, and that way it starts to look more like a circuit. I'm never reading and writing to the same location, writing to the same location in particular, right? Everything's kind of going forward. It looks like a DAG, like we want from a circuit. Okay, so yeah, so to remove circuit cycles, we're just going to parameterize by time. It's a trick that we've seen before. Okay, so good. All right, so let's try to figure out the size of the circuit. Okay. Maybe I'll just start with the first. I should have hidden the second row. So I've taken some kind of program that runs in some amount of time or something. Now I'm imagining some kind of circuit, which is obviously a little clumsy, but it's just going to copy everything over with every time step and things like this. And now I want to kind of loosely bound how big is this circuit we make. Any ideas? Again, everything's a little abstract, but yeah. Yeah, m plus nt. So what? Okay, so yeah. So on the outside, we'll be multiplying by time, the number of time steps. What is m plus n?
M is like the grid size, I guess.
Yeah, so maybe like the memory gets copied every time, right? So that's one. That's one of the two. Okay, got it. All right, so the size of the memory, maybe that's one, right? That gets copied every time step. And then what would be maybe another source of circuit stuff? Yeah. The size of the CPU. And the size of the CPU is? sort of a trick question. It's a constant in the sense that it's independent of the size of the input, right? Of course, a real CPU has a gazillion parts, but a gazillion is still a constant. Okay. So again, it's all a little bit loosey-goosey, but I could think of the size of this kind of conceptual circuit as the size of the CPU plus the size of our memory multiplied by number of time steps, right? And it's a very conservative thing. All right, now let's come up with a very loose upper bound on how big should memory be, or kind of need to be. Yeah.
It's a function of what exactly? The big trigger?
Yeah, well, yeah, so okay, so first the function of what, but you said the first one. The first one is like maybe the input size. It should at least like fit in the input. That's reasonable, right? How else can I try to bound? So of course, yeah, so naively, like you don't know much about the program, right? So how much memory does it use? But even with the limited amount of information, I think we could come up with some simple upper bounds, like size of the input. That accounts for something, yeah.
Probably still size of CPU, right? It's like size of CPU kind of gives you an upper bound on like how many other things you're going to be getting to.
Oh, size of CPU.
So, I mean, I guess maybe
Well, I think that like a fixed size CPU can address unbounded memory. Because in a real computer, like part of the program, part of the thing you give to the CPU is the location where you're going to write out to and things like this, right? So you can actually essentially address space that's independent of the size of the CPU. Yeah. The number of timestamps, right? So the program is only going to write one location every step. So, you know, any reasonable program, like the number of time steps should give you roughly an upper bound, right? You should be able to read in the thing and you write something new. That should give you some upper bound on the amount of memory you really need. Okay, this is of course very loose, naive. You know, maybe a program is much more compact, but there's still upper bounds. Okay. All right, so now if I start putting all these things together, right? Like, okay, so the size of the circuit is a constant plus this. This is like input size times time. And this is all multiplied by time. And suppose I told you it's a polynomial time algorithm that we're looking at in particular. What can I say about the size of the circuit? So that means time is some polynomial in the input size, right? Like n cubed, n to the fourth, like all your homework problems. What can I kind of say about the size of the resulting circuit? It'll be a polynomial. Yeah, so this is some polynomial in the input size plus polynomial of input size. So that becomes a polynomial of the input size times time, which is also some polynomial of the input size. So, you know, it's starting to look at like, you know, running time squared or something. So it's not great, but it's still a polynomial. It retains a polynomial goes in, a polynomial comes out. So in that sense, I can say that at least in principle, any polynomial time algorithm can be converted into a polynomial size circuit. Okay. If you want to make this more formal, you just have to really open up in like what you really mean by a CPU, just to like make it really clear. But the overall argument will be the exact same. Just adding more symbols. Okay. So in that sense, I can try to argue that, oh, I can think of any polynomial time algorithm as a polynomial size circuit because it's basically a circuit operating on memory. And that memory I can just think of as stamped over time. Okay, it's that time trick that really gets you there. That's a very kind of important part. Okay, so good. All right, so that's the first step of this story. And in the second leg, I'm going to try to argue with similar level of kind of high levelness that every search problem, Hamiltonian path, independent set, all these things that we can recognize a solution, is a circuit SAT problem of polynomial size. Okay. So, all right, here's how I explain it. Okay, yeah. So we have these search problems, and they're characterized really by the fact that, if you thought of all of these as a yes/no question, then all of them have some kind of like certificate or proof that will be very easy to verify for a yes. Okay, so you ask subset sum, can you find a subset that adds them up, right? And then they say like yes. And they say, okay, prove it. And they can just present the numbers and you can check the numbers. So in that sense, that set of numbers is some kind of proof or certificate of a yes answer. Okay, so all the problems we looked at, all the tough problems and also all the easy problems from before, they all kind of have this feature, all the yes/no questions, which is that if the answer was yes, there's some form of a proof that's also kind of polynomial size, like the Hamiltonian path isn't that big compared to the input size, that you could verify efficiently. Okay, and so that's really going to be our kind of more formal definition of a search problem. Any problem where when the answer is yes, you can supply some kind of proof that can be verified efficiently. So it says nothing about finding the proof. It just says something about being able to kind of check a proof. Okay? All these problems are easy to recognize a solution, but might be hard to find a solution. So that's all I'm going to work with, right? Because I want to make some very broad statement, right? I want to claim that all search problems can be turned into CircuitSat. So that means we don't have a lot of problem-specific structure to work with. I'm just going to work with this. Okay, good. So, all right, so who's seen this movie? Please help me. Okay, that's like a third of you. Last year it was none, and it just completely threw a wrench in the lecture. Okay, so what movie is this? All right, and okay, who's on the left? Wait, who's the actor on the left? Yeah, I'm getting old. Okay, so that's Ben Affleck. His character's name is Chucky. He's like a normal guy. And then who's on the right? So he's Good Will Hunting. So Will Hunting is like some kind of mathematical genius who was like a orphan and he gets beat up by his foster parents and stuff. So he has some like issues. But he's also really smart. He can solve all math problems and stuff, right? And then Chucky is sort of like his loyal friend, his whole life, and the one guy that Will can depend on, but otherwise doesn't have any remarkable abilities. Pretty normal guy. And they have fun. They get drunk on the weekends. They go to the batting cages, things like this, right? They sneak into bars underage. Okay, you should watch the movie. So anyway, so we have Chucky, Ben Affleck, regular dude, and then Matt Damon, Will Hunting, Prodigy. All right, so let's say that they have some kind of SAT formula, right? And they're kind of discussing it. And Chucky, Ben Affleck is like, hey, Will, is this formula satisfiable? Right? Because Will can solve anything. So Will, he's a janitor at MIT, so he has access to blackboards, and he thinks about the problem, okay, and he solves it, and he says yes. But no one understands, how Will thinks. And so Chucky says, I don't believe you. I don't believe you. I don't know. I don't believe that it's true. And Will Hunting's like, okay, well, here's a satisfying assignment, right? You're going to set x1 to be false. You're going to set x2 to be true. He'll just give you the assignment. Okay, and Chucky, even with his limited powers, as drunk as he may be, he can still spend time to at least verify the formula. You don't need to be Will Hunting to verify that the formula is true or false. Okay, so he spends some polynomial time, checking and stuff. And then say, okay, cool, I checked it. You're right. It is true. Okay. So now, what does Will Hunting say? For the third of you who have seen the movie, this is the most important part of the lecture. Okay, what does Will Hunting say now? Yeah. No, the part where he lights the thing on and he says, what does he say? He says like, this shit's a joke for me or something? Yeah. No, that was the professor. Professor Lambeau. No, that's a different scene. Anyone else? We can just go through all the scenes in the movie. I wouldn't mind. Yeah. Yeah, well, he first asks, do you like apples? Right? He says, do you like apples? And then Chucky says, yeah. And then he says, how you like them apples? Yeah, so this is a very important part of Will Hunting. Okay. All right, so that would be kind of one of these transactions. Okay. Okay, so that was one weekend. The next weekend, they go out to a bar again. And this time, Chucky has an independent set problem. Okay, so he asks Will Hunting, okay, is there an independent set of size K? I can't figure it out. Is there an independent set of size K? And Will Hunting goes to the blackboard at his janitor job, works it out, says yes. Just like before, Chucky says, I don't believe you. So Will Hunting produces an independent set of size K. And then Chucky, even though he's just Ben Affleck, he can still spend polynomial time and verify that it's an independent set of size K, right? So he says, okay, cool, right? Now Will Hunting, as Will Hunting does, says, how you like them apples? And then this time, he asks him to stop, okay? All right, so that's same kind of deal. All right, so what's on this slide? Okay, so, right, so all the proofs, all these problems that we've been focused on and have been giving us a hard time, they're all problems that have certificates that can be verified in polynomial time. Even Ben Affleck can double check one of these solutions. And all right, so now if I kind of open this up, right, here's a satisfying assignment, let me check, and you're gonna spend some polynomial time, right? That's the kind of central part here, right? So that's some computer executing some polynomial time algorithm, right? So Ben Affleck is a Xerox Alto, and he'll spend polynomial time checking the satisfying assignment before confirming that it works, right? So now based on what we just did, right? We just tried to argue that any polynomial time algorithm can be understood with some, hand-wavy transformation as a polynomial size circuit. So we can take that Ben Affleck portion and replace it with some polynomial size circuit, okay, that on a correct answer will be satisfied, right? So this, Ben Affleck verifying the satisfying assignment is a polynomial size circuit that outputs true. And if it wasn't a satisfying assignment, that circuit would output false. Okay? So underlying all these search problems is basically some polynomial size circuit sitting in there that you're trying to satisfy. Okay, so Ben Affleck is a polynomial size circuit. And, right. So if all I know about a problem, right, the only thing all these disparate problems have in common is that they can be verified in polynomial time, right? All of them, just based on this, and just some kind of regularity of what a computer is, ultimately can be turned into a polynomial size circuit that you're trying to satisfy. Okay? So in that sense, any problem, any search problem, can be recast as a circuit SAT problem. Whatever that checker is implicitly a circuit of polynomial size, and you're just trying to satisfy it. Okay, so that's called the Cook-Levin theorem. You could make the argument much more rigorous and, not based on Good Will Hunting, but that is the argument. Okay. All right. So first, any questions about the movie or the proof? All right. Yeah. Okay. So yeah. So our diagram now looks something like this. You give me any polynomial time algorithm, I could turn it into a circuit SAT problem by kind of unrolling the polynomial time verifier. And I could feed it into my black box for circuit SAT. And if I could only solve circuit SAT, I could solve any search problem. Okay. This might be kind of believable because we already saw how SAT could start approaching a programming language. So you can imagine kind of growing that out, and maybe that's implicitly also what's going on. Okay, but this is just one way to maybe prove something. Okay. Yeah, so to make it rigorous, you really want to define what a computer is, and that's where the Turing machine definition comes in and stuff, etc. Okay, but what does this all mean? Right? If we start putting everything together, like maybe at the top, I'll start with an independent set or Hamiltonian path problem, right? Up here. And we know that can be turned into some kind of circuit, right? Okay, so if you could solve circuit SAT, you could solve Hamiltonian path. But we also did in the, kind of the very first lecture, we showed how circuit SAT can be solved by like SAT. You could take a circuit and turn it into 3 SAT with that assignment trick. Okay. And in the last few weeks, we've been doing all these clever things. It's like, oh, you could take SAT and turn it into Hamiltonian path. Okay, and that would be kind of the third leg of this circle. So you start putting all that together. And it's like, if you can solve any of these problems, you automatically solve all of them, right? So in particular, we never directly showed that like Hamiltonian path can solve independent SAT. But now you could start with an independent SAT problem, turn it into circuit SAT, turn it into 3 SAT, turn it into Hamiltonian path. And vice versa, you could start a Hamiltonian path, work your way around and turn it into independent SAT. So they're completely equivalent as far as trying to get a polynomial time algorithm. Right? So there's, we only covered a few examples. There are so many problems out there that would seem so practical and so simple, and we could never solve. And to find out that they're all equivalent, and at some level, like if you're just trying to solve independent SAT, you're like, yeah, I can figure this out. Like, I'm pretty clever. But if you're trying to solve every problem all at once, then you're like, maybe I don't want to, right? But it's sort of like an earth-shattering revelation for computer science to have all these hard problems, we couldn't make sense of it, and then to show they're all equivalent, right? What a surprising outcome at some level that we're at this stalemate. So now there's this terminology for this class of problems. I made this amazing slide today. I hope you appreciate it. Okay, so the terminology is MP. You've probably heard like MP complete, MP hard. What does MP stand for? It does not stand for not polynomial, which is what I often think of. It stands for non-deterministic polynomial time. What the hell does non-deterministic computation mean? So like, imagine you're like writing a brute force algorithm for SAT, right? You would, you probably write some kind of loop where like, okay, first I'm going to explore setting x1 to be true, and afterwards I'm going to explore x1 being false and kind of like recurse, right? And that would take like 2 to the n time, but it would work, okay? So in non-deterministic computing, you're allowed to explore both branches simultaneously. So it's like, if you have some choice like x1 true or x1 false, you imagine like duplicating the computer, and this version of the computer is going to focus on x1 is true, and the other version of the computer is going to work on x1 is false. And that will be one step of a non-deterministic computation. Okay? And then from here, you can move on to x2. Right? So all this kind of brute force things, this branching is just one step in a non-deterministic. So you non-deterministically explore both branches is sort of the terminology. Okay? And x2 and so on and so forth. Okay? So each of these columns in non-deterministic time represents one step. Even though if you were doing it sequentially, you'd have to do all the branches, one after another and stuff. Okay? So as long as you're doing polynomially many steps along here, that would be non-deterministic polynomial time. Okay? And so all of these search algorithms, if all you know is that there's a proof and a verifier, you can always have a non-deterministic algorithm that basically guesses all the bits of the proof. Just like this is doing. It's guessing the first variable, guessing the second, guessing the third. So any problem with like a proof of polynomial size can be solved in non-deterministic polynomial time because you just keep branching where you guess each bit of the proof. At the very end, once you have a whole proof, right or wrong, then you do some polynomial computation to verify it. Does that make sense? This was, I don't really know if this matters anymore, but this was something that the complexity theorists are, it's the early days. They're coming up with models and they're thinking of different ways to think about computing. In any case, that's where the terminology comes from. So all these search problems are also the same as the problems that are in non-deterministic polynomial time. Right? So basically, if any of these come out true, then the whole thing comes out true. And if you have a problem that has some non-deterministic polynomial time algorithm, you can always get a certificate based on which branches led to the true solution. That makes sense? So if you knew the branches of this non-deterministic algorithm that leads to the right answer, that could be your proof, where then sequentially you can just run through and execute those particular steps. If that makes sense. Anyway, so that's just some terminology. It doesn't really change the content of what's going on. So, okay, so, right. So the fact that Hamiltonian path, an independent set, is in NP, it has a certificate, is why it can be solved in circuit SAT. So anything that has a search problem is called NP, non-deterministic polynomial time. Okay, but you can just think of it as a search problem. And then any problem that can solve circuit SAT or can solve SAT, right? Any problem that can solve SAT can solve all problems in NP because we just showed that any NP problem can be solved by circuit SAT and SAT. Okay, so if a problem can solve any problem in NP, it's called NP hard. It's in the class of the hardest possible problems within NP. Okay, and if you're in NP and NP hard, you're called NP complete. So you have this complete class. You have these problems that are in NP, they have non-deterministic polynomial time algorithm. They're search problems, but they can also solve all other problems in NP. So NP hard means it can solve all other problems in NP. Doesn't mean it's in NP itself. And then NP means it's a search problem, okay? And that's where you get this NP complete thing. All these problems are equivalently hard. Okay. And kind of the big open question of our time is, does P equal NP in the sense that, are there polynomial time algorithms for this, or can we prove there isn't? Okay. Yeah.
So a problem that would be NP hard, but not NP complete, would be something that has like the exponential time certificate, right?
Yeah, or at least doesn't have a polynomial size certificate in any case. So like, I think a problem like, given a SAT formula, count the number of satisfying assignments to it. That would solve the SAT formula because you just want to know if it's non-zero. But like a certificate, it's not clear what like a polynomial size certificate is. If you're counting all the assignments, it's going to be exponentially many assignments. You can't like rattle them all off, in polynomial size and things like this. So some of these counting problems are, for example, these things that show up. There's a lot of contrived problems. Yeah, so there's stuff beyond kind of NP. And then you could take, complexity. They should hopefully explore this stuff. Okay, but the big question is there a polynomial time algorithm, or can we prove there isn't? At some level, this sort of clarifies the problem. We have this kind of strong equivalence class, right? Okay. Any questions? Yeah.
Do you think P equals NP?
Do I think P equals NP? Well, my opinion doesn't really matter, but I guess I'm guessing no. Yeah. I don't know what's that worth, but it, huh?
Do you think we'll prove it
in our lifetime? You're not the first person to ask in this class. So what did I say before? Yeah, I don't know. I mean, I think, well, so let me give another question of an example of a question that we could answer, right? There's a different question of, is everything computable? Like, at some level, you can formalize this, but does every yes/no question have an algorithm that might take forever, or take a really long time, but in some finite time arrives at yes or no? Okay, and this is like a very almost practical question, because if I give you some source code, you want to know if there's infinite loops in it and stuff like this, right? So the question of basically is any kind of natural yes/no question computable was posed around 1905 or something by Hilbert. Hilbert famously gave like 20 questions to challenge the math community. He was a famous German mathematician. And this was one of the questions, it's sort of more in the logic space, right? Are all questions, computable? And this was before computers, but like math was becoming much more, they were doing much more rigorous kind of proof lemma, that notation kind of came out of the German school in the 1800s. And so it's starting to look more and more mechanical, and they're saying, oh, can you kind of mechanically address any question ultimately? Right? And there were several, and what's amazing is that kind of like crazy question, we actually answered. Okay, and this is what Turing solved, and also Church solved 1 year before him. Okay, so Church kind of did some kind of more mathematical proof where he's like, oh, I'm going to think of computation as applying functions and applying functions and applying functions. It looks a little bit like a functional programming language or something. You don't really think too much about the underlying mechanics. And it looks algebraic, basically. It's a little harder to read. And Turing, as probably pretty closer to your age than mine, and maybe actually your age, he didn't know about Church's work, but he sort of said, oh, well, what does computing mean? He said, well, imagine something that looks like a typewriter or something, and it has some like endless ticker tape of memory, and you can write things, you can read things, you can write things. So the first thing he does in his paper is kind of propose he didn't call it a Turing machine, but propose some kind of machine that models computation. And it basically looks exactly like a modern computer in terms of having some kind of like processor and reading and writing to memory, but very primitive. Like you're working through a ticker tape and you can only go left or right one step at a time, or read and write in one spot, something like this. Imagine like a trolley car or something. And that was the first part. And then he points out, okay, not only that, but this machine can run any program in the sense that like you can fill part of the ticker tape with the program, and then you can read off the instructions of what to do with the rest of the computer, right? So just like your computer can run any program, it's a universal general computer, okay? And then he basically does something called a diagonalization proof. I don't know if you guys have in your math class, like, okay, we're just going off on a tangent, but like there's this question of like infinities, right? There's different kinds of infinities. So in particular, like there's this notion of countability. So if you can enumerate things, no matter how, even if it's infinite, but you can at least number them off, that's called countably infinite. So the natural numbers are your canonical example. It goes to infinity, but you can kind of go 1, 2, 3, 4 and not miss anything, right? And anything that you can number sort of has this property, right? But then Cantor pointed out that you can't number all the real numbers, okay? And there's a very, very short, simple proof. It's easier for all of you because you're in computer science. So imagine you could write out all the real numbers. There's a first number. I mean, you can count them off, right? You could enumerate first, second, third. So, okay, here's the first number. It's like a bunch of zeros. And I'll put a 1 there, So imagine listing off. So this definition of infinity, countably infinite, means you can enumerate them. You can actually list them in some particular order and not miss anything, okay? So treat every number as, infinite length bit string. And then just write them down in a list, okay? And supposedly this includes all possible real numbers if real numbers were countable, right? But there's at least one number missing. So imagine I write this whole table, it goes on and on and on. But there's one table missing, one number you can point to that's missing in this table. Which is it?
The sum of two of them divided by two.
The sum of two of them divided by 2? I don't know, that could be later in the table, right? Yeah.
Flip the first digit of the first number and the second digit of the second number and third digit.
Yeah. So if you just go on the diagonal of your table and you flip all the bits, it's not going to be in your table. It's not in row 1 because the first bit's wrong. It's not in row 2 because the second bit's wrong. It's not in row 3 because the third bit's wrong. Right? So this was called diagonalization proof. And this was just like shocking in the 1800s. Like, it's like before electricity, right? Like, so, and yeah, I think Cantor eventually like has a mental breakdown. Like, this is like wild stuff. And so Turing essentially showed he basically gave a diagonalization proof. And you know, at some level, the question that you can't compute is, given a program, will it terminate on all inputs? And I think a really important ingredient is that when Turing took like computation and made it this kind of mechanical thing, right, where it's a ticker tape, he also showed that all programs can be expressed, you know, with bit strings at some level. So you can enumerate all possible programs because all programs are represented by some source code, right, some bit string, which means you can list off all the programs that you can answer this question for, and then you flip the diagonal and you get some program that, yeah. So he also did this proof by contradiction, this diagonalization style proof. But the key part was establishing, this is really taking the wind out of the sails. The key part was, you know, establishing some model of a computer so that you can think of, you know, programs as bit strings so that you can do this flip the diagonal trick and reach this contradiction. Okay. And of course, the legacy, of course, is that, you know, John von Neumann saw, of course, this paper because, you know, in Church's words, Turing was able to give a direct proof answering this question, whereas Church's was kind of this crazy abstract mathematical proof. And then von Neumann looked at that paper and he based his early designs of the, what was those first computers called again? They were made at Princeton. Okay, what? Yeah, the ENIAC stuff. That was a universal computer based on Turing's design. But you know, back then they were thinking of, because before they were making computers that did specific like bomb calculations or something, like the computer was built for something specific. But the idea of a general purpose computer where you could load in the instructions and the computer can simulate, that was from Turing. Okay, come on. Okay, enough of that. Any questions? So I know it's very distracting. It's a major bummer. All right, whatever. Okay. 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 Have you guys seen that movie? You're all gonna say no. That's Jerry Maguire, which is another movie that probably your parents have seen and you have not. But in any case, okay. So I wanted to mention this paper. So we talked about the Cook-Levin papers, and then a year or two later, Dick Karp at Berkeley comes up with this paper, reducibility among combinatorial problems. And that's really what we've been doing for the past few weeks. But if we just look at like the abstract, right? Okay, I mean, this is just like a banger. So like a large class of computational problems involving, you know, the determination of properties, graphs, you know, and it'll say something like, okay, language recognition problems, right? Some kind of search problem. And okay, it's reasonable to consider such a problem satisfactory when it's solved within a number of steps, polynomial in the length of the size of the input. This is so old that even this was slightly debatable. But then look at this last sentence, right? We show that a large number of classical unsolved problems in matching, packing, routing, assignment, sequencing are equivalent in the sense that either each of them possess a polynomial bounded algorithm or none of them do. Okay? And right, all the general methods for all these problems require a combinatorial search that grows exponentially in the size of the input. In this paper, we give theorems which strongly suggest but do not imply that these problems, as well as many others, will remain intractable perpetually. Right? So this is like a massive, massive, massive paper. And, you know, polynomial in the size of the input, you know, if these problems do possess polynomial bounded algorithms, a Y class, then they all do. Then he talks about like Turing machines and stuff. This work was stimulated by the the work of Stephen Cook. So Cook was so there was Cook and Levin, and they both came up with this argument that any polynomial time algorithm can be turned into a polynomial size circuit. But Levin was in Russia on the other side of the Iron Curtain, so we weren't aware of Levin's work. But Cook was a colleague of Karp at Berkeley. And they talk about the class P, various things, determinist algorithm. They're being very formal. One tape Turing machines. Just so on and so forth. So this is like some massive paper. Maybe the one thing I want to point out is that this is from 1972. Yeah. And I would say up to that point, there was real hope because we were making progress on some problems, including some of the algorithms we saw in class, like, linear time strongly connected components or something, very clever algorithms. And we're always hoping we're going to come up with more clever ideas at that point in time. Okay, good. So he lists all these problems that you see. Here are some problems that you can solve. 2SAT. We're going to do minimum span trees next week. Shortest path. Yeah, so the other problems we'll do later in this class. Non-deterministic algorithms. Yada, yada, yada. What am I looking for? I'm looking for this one. Okay. So he gives this huge list of problems, some of which we haven't seen and we'll see more in coming weeks. All these problems are complete. Satisfiability we did. Directed Hamiltonian circuit, undirected Hamiltonian circuit, 3SAT, all these things. And he somehow, as a typewriter, he made this amazing picture where all these lines are sort of how he did the reductions in the paper. So he went from satisfiability to click to node cover. And so we'll end up covering most of these by the end of the class. Or maybe half, I don't know. In any case, on the exam, you're given a whole list of these. So you don't have to. All right. Good. Partition, that's from your homework. Oh, I hope that didn't give away the homework. All right. Okay, so that's one thing I wanted to do. Okay, some high level comments. I've often said, all of our problems are solved essentially in one of two ways. Either identifying the right subproblem, things like divide and conquer, things like dynamic programming, or changing the input. Okay. And at some level, when I look at this sort of MP completeness Lion King thing, to me, like, this first leg that we spent a long time on, they're all reductions, right? So they're all about changing the input, right? Taking SAT, changing the input into independent set, something like this. And in the second leg, the key, I think ingredient of that Cook-Levin thing was to parameterize by time, right? Just adding this time index like we did for Bellman-Ford. And this is like very similar to all of these identifying the subproblem type stuff that we had been doing. Okay, so just these like very basic styles of thinking, slightly non-intuitive. Or at least to me, it was non-intuitive until it was kind of beaten into me. Have very large implications. Okay. So, okay. Any questions? Yeah.
NP hard, but not NP complete. What necessarily does that mean? Like, if we can solve SAT, we can solve the problem. But if we solve the problem, we can't solve SAT.
Okay. So if a problem's NP hard but not NP complete, what does it mean? So it directly means that it doesn't have a polynomial size proof and verifier. Now, if it's NP hard means it can solve any problem in NP. So in particular, it can solve SAT, and SAT can solve everything else. But if it had a polynomial time verifier and proof, then SAT could solve it, because of this Cook-Levin trick, at least in principle. So the NP hard problems are generally the problems that can solve SAT, or if they're not in NP complete, but SAT cannot solve it. Yeah, it's another, they all kind of come out equivalent. Yeah, I'm not even sure if the names really matter. I mean, they're like a shorthand. What you really want to know, right? At the end of the day, I have some problem that I'm interested in. Can I come up with an algorithm or not? That's what really matters. And this is like a very strong answer to a very large class of problems. And then beyond that, you're just like, giving names and stuff to stuff. writing Wikipedia articles that make it seem fancy. But there's a a very basic question that drives all of our kind of inquiries. Can I solve this problem on a computer or not? That's what really matters. Any other questions? Okay, so first of all, you're welcome to relax if you want. Just go. Okay. Okay, so I have queued up, so I thought we might have some time. A problem that I didn't quite get to last class is another one of these kind of very clever reductions. I think you were already exposed to it if you went to your PSO. Okay, so the problem is graph coloring. This is another one of these canonical, famous hard problems. So I won't even do a poll. We know it's hard. Okay, but you're given a graph like this, and your goal is to color it, the vertices, with as few colors as possible, so that no edge has like the same endpoints as the same color. Right. So for example, like if you had a bunch of like cell phone towers, you want them to use different frequencies, like adjacent cell phone towers to use different frequencies, so they don't like cross whatever they do. So that's like assigning different colors if you think of each color as some kind of part of the spectrum. So yeah, okay. I've prepared a solution. So this would be like 4 colors, and I couldn't figure out how to do it in 3 colors, but maybe it's possible. And actually, there is a way to argue that you can't do 3 colors, but can anyone see it? I remember somebody pointed this out last year. Yeah, so in the top right, we have 4 vertices all connected to each other. So that would require 4 colors. So I don't think we can do better than 4. Okay. All right, so good. All right, so we're going to try to show, we're going to use our fancy new words. We're going to try to show that 3 coloring is NP hard, which means that it can solve SAT and circuit SAT and thus everything else in that circle. It's easy to see that it's in NP because you can just give me the coloring and I can check it's good. Okay, so we're just going to focus on 3 coloring. That's the smallest K, where it's NP hard. You'll find that 2 is not so hard to do. And as an intermediate problem, we're ultimately going to go from 3 SAT to 3 coloring, but in between, we're going to do a slightly more general problem quickly called subset 3 coloring, or list coloring is really what it is. So it's like coloring, except for every vertex, I'm going to give you like a list of colors that you're allowed to use, not necessarily all 3 colors. Okay, so first of all, if it doesn't have anything written, that means it can be any one of the 3 colors. But like in the bottom left, this vertex can only be given colors 1 and 3. This one can only be given colors 1 and 2. Okay, so it's like a little bit additional input, and that flexibility will help us when we do some conversions. Okay, so we're going to show that subset 3 coloring can solve 3 SAT, and then we'll show how 3 coloring can solve subset 3 coloring. Okay, so I guess we're going to do the second leg first, so I lied. All right, so the first thing we're going to do is we're going to start with list coloring or subset 3 coloring, and we're going to show that 3 coloring can solve it. Okay, so somehow you're going to be given a graph that's also annotated with these lists, and you're going to create some kind of graph without the lists. It'll probably have to be different. And then you're going to feed that into a black box that doesn't look at any lists, okay, but somehow gives some yes/no answer that's useful. Okay, so that's the high-level approach. And all right, well, okay. Any ideas? In fact, if you went to PSO, you might have gone very close to doing this. Yeah, so the challenge is somehow, you want to create some kind of graph where there are no lists, but still somehow encodes.
Like for each of the vertex, we connect like another vertex to it.
So it'd be, so, okay, so I want to connect this vertex to another vertex. So it'd be very nice if I knew there was a vertex out here that had to be colored 1, so that I could attach it to here, and then this one cannot take the color 1, right? So we don't quite know how to do that. Maybe we'll figure that out in a moment. But if I could somehow like guarantee there's vertices that have to have like color 3 and color 2 and stuff like this. Okay. So if I could somehow create 3 vertices that occupy the 3 colors, then I could, and somehow enforce that, then I can attach them to these to say, 1, 3 means you can't use color 2. That's why you're connected to that vertex that has to have color 2. Okay. But of course, up here, we sort of have a very small version of our list coloring problem where each of these vertices are given a list of size 1. So now how can I sort of enforce that they will take on the 3 different colors? Yeah.
Make like connects the 3 you just added all together.
Okay. So I'm going to connect the 3 together. Now they have to have 3 different colors. And I'm just going to interpret one of them as color 1, color 2, color 3. Okay. So you have something like this. Y1, Y2, Y3 have to have distinct colors. So just decide, I'm going to call Y1 color 1. And then you're going to connect everything just like this. Okay. And then once you do that, you can actually erase the lists on them. Okay. So if someone can actually color this graph with no lists, then you just interpret Y1 as color 1 and then the same color wherever it appears down here. Okay. So if you can color this graph, then you'll recover a list coloring that follows those rules. Okay. So that's the idea. If you can do a 3 coloring on this graph, I mean, I think of it as like that triangle as like an artist's, what do you call that? Color palette thing? You know how they hold like rip, whatever that I don't have the words, but you know what I mean? So I think of this as like the color palette. And when I draw the line, I'm saying, oh, that has to be this color. That has to be that color. Okay. All right. So that's a cute one. And that will ultimately, I didn't mean to. Yeah. So you do something like this. So you take your annotated graph, you do this color palette trick, and now you can feed it into this black box without the list there, because that's being enforced by your kind of triangle. Okay, so that's one leg. Now I guess we just have one thing left to do. So now if I can use subset coloring to solve 3-SAT, then ultimately coloring can be used to solve 3-SAT. This part, it's a little bit trickier. So, right, so somehow I want to take a 3-SAT formula, turn it into a list coloring problem so that I can feed it into my list coloring black box, which I already know how to implement with regular coloring. Okay. All right. Any ideas? Actually, this one's super tough, but I shouldn't discourage you. Okay, fair enough. We don't have that much time anyway. So the first step, I think, is that I'm going to give some like meaning to the colors. I'm going to think of one color as like true, coloring a vertex true, coloring a vertex false, and then somehow some third color, which I interpret as neither. It's not true, it's not false, it's... What's this? Truthy is what they said on the Colbert Report once. You guys probably never watched the Colbert Report. That's okay. Forget it. All right. So, okay. So for every variable, I'm going to set 2 variables connected by an edge. Okay. And they're going to represent the 2 literals, xj and xj bar. Okay. And I'm only going to allow these 2 to be set to true or false, because I really want to set xj to be true or false, and then the opposite one, xj bar, has to be false or true corresponding, right? So that will kind of just be enforced by one of these edges for every vertex. For every vertex, I've now added a pair. It's like some kind of ladder. Okay. That one might have been guessable. All right, this is where it gets a little more wild. Okay, so let's say I want to somehow encode this clause, okay, as some kind of list coloring problem. Okay. Then we're going to make something that looks like this. So, for x1, I had created some vertex a1, and for x2 bar, I had created some vertex somewhere a2 bar, and some vertex x for x3, I'd created some other vertex a3, and somewhere out there's also an a3 bar, an a2, and a1 bar. And somehow I'm going to connect them up like this. There is a way to understand what's going on. But, so we have basically this gadget here, where all these vertices can be true, false, true, whatever is allowed in the root. Okay? And somehow, this gadget, you should only be able to color this whole gadget, which in particular means you can set the root to be true, only if somehow the colors assigned to these satisfy the clause. Right, so these are already from our previous step constrained to be true or false. Okay, and somehow this gadget is set up so that you can only ultimately color the whole thing and set the root to be true if either this is true, or this is true. Okay, some like crazy gadget. Okay, so how do you reverse engineer this? We just need to figure out how to do a pairwise OR. Okay, so take this gadget here. So I have A, B, and then kind of true, false, and true, false, and true, false. Okay. So this lemma says that for this like simple looking graph, I can only set C to be true if either A is true or B is true. In particular, if they're both false, I shouldn't be able to set the root to be true. Okay. And if I can do or between two variables, then I can start combining it to deal with three. And I think here, all we do is just check. Okay, so the claim is that if these are both false, I shouldn't be able to make C true, right? So we can just go through it, right? So like, what should I color? All right, so your goal is to see if you can figure out how to make C colored true. So like, what could this one be? This can be false or neither. And then same with this one. Oh, wait, no, this can't be false. Oh, well, okay. Well, if you just told that these two are false, sorry. Okay, yeah. So if this is false, then this can't be true, and that can't be true, right? So both of these can only be either false or neither. So in the symmetric, so you can pick either one. Maybe I'll put false here. I just lied. True here and neither here or something, right? But because you have the true here, you can't set C to be true. You have to set it to be false. Okay. But if this was true and false or something like this, then you could have put a false here and a neither. And then you could have gotten your truth on top. So this gadget is kind of doing exactly what we want. And ultimately, that crazy gadget from before is, if you look at it closely, it's just combining two of these OR gadgets, right? So one becomes the input to the next OR gadget. And in here, I'm saying, look, the OR of ORs has to come out true. That's when I restrict the list to T up here. And so that's how we encode our clauses. Okay, I'm over time. So you put that all together, and 3-SAT can be solved by subset coloring. You already showed that subset coloring can be solved by coloring, and now SAT can be solved by coloring. Okay, so that's going to conclude sort of this MP hard, MP complete leg of the course, and then next time we'll kind of be good old-fashioned algorithms again. We'll do something called minimum spanning tree.